Hello and welcome. I'm Philip, and in this section in between video I want to cover everything about perspective that you ever wanted to know at drawing, and probably much more. We will dive to the ground of the theory about perspective. There will be very many details and also a little math. If you just came here for the quick use of vanishing points, have a look in the description when I get to that. For those who watch everything, in the end of this video you will have understood what parallel perspective, linear perspective and fisheye perspective are. You know their limitations and why it may be argued that fisheye perspective is more natural than the linear perspective that we are used to. Vanishing points play a crucial role, especially in linear perspective, and there is also a relation to the center point, that is the middle of your image. These points cannot be placed arbitrarily, and I will show you easy rules that give restrictions on them. Following these rules will give you an astonishing impression of space as you see. This video covers the theoretical background of perspective. Some of this theory I consider to be crucial, or at least very beneficial in order to get along with perspective drawing, and some is supposed to just be a crutch that you can use when you are sitting in front of your image and you just cannot tell what went wrong. I provide you like a sandbox where everything is 100% correct if you want it to. But I don't want to fool you, and I really have to stress this. After you understood these theoretical backgrounds, the next step will be to emancipate from them and build an intuition. You can draw in perspective solely from intuition, but drawing solely from theory you will have a hard time. Intuition is what you really have to learn in the end. Theory may just help you to get there faster. How to get a feeling for space and to develop spatial imagination will be the subject of part 2. But now for this video it's theory. Let's start with a little motivation. Have you ever tried to draw your surrounding? Start at one point and draw on and on and on, with no construction lines and just with looking at what you are drawing? If you did, it may have happened that you lost the faith in your redrawing skills. When you went on drawing further away from the point where you started, you may find that there is too much space for the things you need to fit in there, and straight lines you began at another spot suddenly seem to have a wrong angle. Don't worry, there is nothing wrong with your redrawing skills if you notice that at the rim it gets confusing and nothing makes sense anymore. This is an inherent problem when redrawing your surrounding, or rather, this is just how it is. Actually, there are artists that draw intentionally and from imagination in this so-called fisheye perspective, the most well-known probably being Kim Jong-gi, and I also learned to love it. But when I first noticed the problem with the angles, I was totally confused, up to even despaired. In case you did not attempt to draw your surrounding, I tell you what I mean. If you are straight in front of a wall that expands infinitely to the left and right, and you begin to draw it, it may look like this. There are parallel lines. Now you go on drawing the wall and look towards the left. Look at the spot you want to draw and draw what you see. I guess now you all can see the problem. These lines that were initially parallel when you looked straight at the wall got bent, and they are bending the more you digress from your initial view. Although the wall has physically perfect straight outlines, they visually get bent depending on where you are looking at. This may seem obvious, at least there is nothing unnatural with it, since we are seeing the world this way for our whole life. My problem was that this did not correspond with the linear perspective that is everywhere taught and which I took as this is how it is. Linear perspective, put simple, means lines that are physically straight are straight on the image too, and objects that are far away appear smaller. This is also what we are used to from pictures and films most of the time. 99.9% of all images and videos you ever saw are in linear perspective. So now we are at the point where basically everything we know is in this linear perspective. But on the other hand, we have the undeniable observation of physically straight lines that are not straight on the image. And this is no arbitrary digital computer program distortion. This is our very own vision and how we perceive the world, with our own eyes. For sure, you can feel the headache this gave me, at least you could pretend to do so. Actually, it took me years to get out of this rabbit hole and understand this seeming paradox. After many hours of research, giving up, resuming again, etc., I still couldn't find a solution. But eventually, I found a tutorial from an artist called Nzio that made me understand what a vanishing point is. I mean, somehow everybody knows what it is. You place 3 of them on the paper, draw the guidelines, and then you can draw a cube. But what it really is, somehow nobody knows. Now let me give you a little hint on how to solve a paradox. It has to do with different kinds of projections to produce an image. While the concept of vanishing points is not connected to a particular projection, understanding them was a huge step to solve my paradox. In fact, this was probably the most essential key moment on my journey of understanding perspective. So let's discuss them now. What is a vanishing point? Is it a point in a two-dimensional canvas or a point in the 3D space you are drawing? Fasten your seatbelts, ladies and gentlemen. It's neither. Actually, a vanishing point is a point on the surface of an infinitely expanded sphere in the 3D space with you, the viewer, as center. You might also think of it as a direction in 3D space. Furthermore, a cube does not have 3 vanishing points, he actually has 6. There's one for each direction in space his edges point to, and a corresponding one at the opposite. And where these lines hit the surface of the sphere, the vanishing points are. The vanishing points of this cube, for instance, will be here on the sphere. And other geometrical objects have different sets of vanishing points. A cylinder, for instance, has only 2 vanishing points, and they are located where these lines hit the sphere. How these points are gonna come onto your canvas and help you drawing, and why in the case of a cube there mostly are only 3, I will talk about later. Let's call these lines physical guidelines. So a cube in the 3D physical world emits 3 bundles of these guidelines, or 6 depending on how you want to put it, and in infinity they hit a vanishing point. If you turn the cube around, his guidelines move, and the vanishing points move accordingly over the surface of the infinite sphere too. And if you move the cube around without turning, his guidelines obviously move around. However, they do not change their direction and the vanishing points stay exactly where they are. The reason for this is that the sphere is infinite and therefore the finite movement of the cube is negligible and doesn't move the vanishing points on the sphere. If on the other hand you move or turn around, the vanishing points and the guidelines stay at the position where they are. This guideline did not change its physical position or direction, and if we look up again, there still is the vanishing point on his place on the infinite sphere where he was before. And you can explain all of this just by imagining the guidelines as real physical objects, maybe endless strings or laser beams. And also the vanishing points, imagine them as real physical objects, infinitely far away. Basically the end of the guidelines, but still having a somehow physical position on the sphere, and they can move on it if the cube is turned. If you look in their direction, you can see them just as any other physical object. So although vanishing points are not part of our 3D space, in many aspects you can treat them as if they were usual physical objects in 3D space. You can look at them, have them on your image, or you can turn away and not see them. But you need to understand that in the first place, they are not a point on your paper where you draw or a pixel in a digital image. These are just images of vanishing points in the same way as this is just an image of a real basketball. Or would you insist on this being a basketball? Can you have fun with it? No. This is just a picture which happens to show a basketball, and this is just an image which happens to show a vanishing point. The basketball is an object located in my garage, and the vanishing point is an object located infinitely far away. And both can be observed by a photograph or a drawing, for instance, and both can be moved. The basketball if you throw it around, and the vanishing point if you turn its corresponding cube. Now let's take all a deep breath. If you need a break to ponder about all of this, that's fine. I expect no one to understand the true nature of vanishing points right off the bat. As I said, it took me years to figure it out. And if you understood what vanishing points are, that's good news, because this probably already was the hardest part of this video. Now let's think about how we can build a bridge from this abstract theory about vanishing points to their use at drawing that everybody knows and uses. In order to do so, we need to raise the general question how images are derived from the real world. The answer is by projections. There are countless projections for different purposes, and you can see a projection as a rule by which the 3D world is reduced or projected onto a two-dimensional image. In the following we will discuss 3 different kinds of projections. The 3 images here each correspond to one type of projection and may give you a quick hint on their basic properties and differences. They all are related to each other and can be transformed into another. Linear perspective is the most common projection, but as I said, fisheye may be even more natural. In both, vanishing points play a big role, especially in linear perspective. And maybe you remember, one half of our paradox was about linear perspective, so we really want to understand it. But first we will discuss parallel perspective. It's the simplest one, and understanding it may make it easier for you at the other two. Remember, a projection is a rule by which the 3D world is reduced to a 2D image. What is the rule for parallel perspective? In parallel perspective, there is a plane in space we call the canvas. And here we have an object we want to observe. In order to do so, we need to follow lines that go through the object and hit the canvas perpendicular. These intersections with the canvas yield our image, which will look about like this. Producing an image this way causes that lines that are physically parallel will be parallel in the image too, and it also implies that objects that are farther away are not scaled down accordingly on the canvas, like we otherwise are used to. The depth of the image is gone. Seeing something in parallel perspective is like being infinitely far away and at the same time zooming in infinitely close. In real life, you can watch an approximation of this effect, for example at soccer matches, when there is zoomed on a particular player. Even when he walks towards the camera, he won't become significantly bigger because he is so far away, and when another player walks around, you hardly can tell which player is closer to the camera. That is parallel perspective. Most computer games that are not in 3D are in parallel perspective. This was a nice warming up. Now comes linear perspective. As I told you, basically everything we know from images and videos is in linear perspective. Many computer games are in it, and also in art, linear perspective is omnipresent. What is linear perspective? In linear perspective, the rule to get an image from the 3D world goes like this. There is some beholder, and here we have again the canvas, like in parallel perspective, and an object to observe. The lines from the objects in the world now, however, don't go parallel through the canvas, but they all go towards the beholder, that is you. The intersections with the canvas produce again the image. It is easy to imagine that physically straight lines will be straight in the image too, but you also see, unlike in parallel perspective, physically parallel lines are not necessarily parallel in the image. But as a side note, if you were to move the beholder very far away, the lines will become parallel and we end up in parallel perspective again. So you might think of parallel perspective as a special case of linear perspective. And not only can you project real objects onto that plane, but also vanishing points. Here we have our infinite sphere, and inside of it there is the beholder and the canvas. Over there is a vanishing point, and he can be seen here on the canvas. And over here is another vanishing point, but we cannot see him at the moment, because there is no intersection with the canvas, and therefore he is out of our field of vision at the moment. With a little spatial imagination, you can see that from this kind of projection, the known behavior of vanishing points arises. Physically parallel lines look on the image like they are drawn to the vanishing point that lies in that direction. To convince ourselves about that, look at our picture taking. There we have our vanishing point. Now any line that is physically parallel to the line of the vanishing point will look on the image like it is drawn towards him. Let's for example look at a chain of cubes that goes in the same direction. Their vertices along the edges can be seen here on the canvas. Try to imagine what would happen if you continued this chain of cubes. The projections of their edges would move towards the vanishing point on the canvas. And this is exactly what is happening here. All lines that are parallel to the line of a vanishing point look in the image like they are drawn towards him. And that is just a simple cause of how linear perspective is defined. And because Minecraft is in linear perspective, we can use this as a nice example. If you look around, vanishing points might leave your vision and new ones come in. But you see, even if they leave the image, they still draw in edges that go in their direction. I guess this is what you are used to and are familiar with. Notice that they can lie very far off, up to infinitely far away as you see, when you are looking perpendicular at the corresponding guidelines. In order to still be able to talk about outlying vanishing points, let me introduce the view plane. You can think of it as an infinite extension of your canvas. Your canvas is just a small part of it, and of course the canvas is limited due to your vision being limited. Vanishing points, as I mentioned, can be arbitrarily far away. They can lie anywhere on the view plane. And don't get confused, the vanishing points on the view plane, of course, are just projections of the real vanishing points from the surface of the infinite sphere. However, everyone calls the ones from the view plane vanishing points, and so from now on I will do that too. And when I mean the vanishing points on the sphere, I will speak of true vanishing points. Okay, I think now you have a good impression of linear perspective. You know objects of the 3D world are projected linearly onto the canvas with respect to the beholder, and there is an infinite extension of the canvas, which is called view plane, and which contains the vanishing points. And the vanishing points on their own are also projections from the true vanishing points onto the canvas or the view plane. And you can use them to draw the projections of physically straight lines, for example from cubes or cylinders or whatever. And remember, one half of our paradox was about linear perspective, so right now we just took a big step to solve it. Now let's get to the third projection, the fisheye and its curvilinear perspective. It's more complicated and there are countless variations. One approach that leads to a fisheye is the demand that objects that are far away should appear smaller on the canvas. I guess this seems very reasonable to you, and to some degree this is the case at linear perspective too. But if in linear perspective you are watching a chessboard frontally, it looks like this. All squares are equally big, although the ones at the rim are definitely farther away from the viewpoint than the middle ones. Now, what happens if you demand that objects that are equal and at the same distance from the viewer should appear equally big on the canvas? Or similar, objects that are equal but different far away must be in a different size on the canvas. For the chessboard, this means that the outer fields have to be smaller than the ones in the middle. And this means there can be no straight lines anymore, and therefore this can be no linear perspective anymore. In conclusion, the reasonable sounding demand for an object's size on the canvas, only depending on its real size and distance to the viewer, leads to skewed lines. And this perspective is a fisheye perspective. Here are some examples of fisheye perspectives. Actually, you can transform fisheye into linear perspective and the other way around. The only thing you have to do is to stretch and bend and compress certain areas. In order to get from fisheye to linear perspective, you have to bend these skewed lines outwards until they are straight. Or you could pull the rim towards the outside to reach the same effect. And if you are in linear perspective, you can do the opposite to get a fisheye. This also means that in fisheye, similar effects with vanishing points appear. Physically parallel lines are drawn to a vanishing point. Only they usually do it in a curvilinear way and not in straight lines. And only physically straight lines that go through the middle of your image will be straight in the image too. All other lines are skewed around the middle, and they are more skewed the more you move away from it. By the way, the more you cut from the rim of an image, the smaller is the difference between linear perspective and fisheye. Yeah, this is fisheye. It looks somehow crazy and strange, and you might wonder why I waste so much time on this fisheye. The reason is what I told you before. It's the inherent problem of drawing your surrounding. Remember the wall. Moving your eyes around and drawing everything leads to a fisheye. Taking eye movement into consideration, the way we perceive the world is no nice and straight linear perspective. It's a fisheye with all its crazy lines. In fact, there are no straight lines. But wait, you might think, why don't I see crazy skewed lines when I look at something? Like for example this. The reason is, they actually are skewed, all of them, besides the ones you are directly looking at. But you only see a very small part of the arc sharply, and so it appears to be straight. In the periphery of your vision, they are not straight anymore, but you hardly can notice without turning your eyes. But if you do, you would see the skewing. Think about the wall from before. So the seeming paradox solution is, probably you all already guessed it long before, drawing your surrounding by looking here and there and draw what you see corresponds to a fisheye projection and not a linear perspective. Linear perspective is not how we see the world with our eyes. I guess now you understand why I focused so hard on the fisheye. I found it when I noticed that linear perspective has troubles if you draw too much. I was thinking that if it goes more wrong the farther you are away from the center of the image, then it must have gone wrong already before, in the middle of the image. I concluded that linear perspective is bullshit. I don't think that way today, and soon the rest of the video will focus on how to apply linear perspective. But I want you to know that this is not how we see the world, and when you draw the world, you will likely end up in a fisheye, which will get more and more obvious the farther you draw. You need to understand that linear perspective is just an arbitrary simplification, at least compared to our own vision. So keep that in mind. Of course, the benefits of linear perspective outweigh these seeming flaws by far, and it is no surprise everybody uses it. It's incredibly useful and easy to apply, and it looks perfectly fine. And also most cameras shoot in linear perspective. Okay, now that you have a big foundation about the theory of perspective, let's dive into the application of linear perspective and vanishing points. First, let's talk about how many vanishing points can be on the view plane and on the canvas. For the canvas, this of course depends on how big you make the canvas, and this is directly connected to the viewing angle. For now, we just take a viewing angle of 60 degrees. Why this makes sense and why it shouldn't be exceeded by much we will see later. But for the moment, this has direct consequences on how many vanishing points can be on our canvas at one glance. And that is, at most, one. With 60 degrees viewing angle, you simply cannot see two vanishing points at the same time because they are 90 degrees away from each other. And by the way, when you look randomly in space, there is only about a 1 out of 3 chance to see a vanishing point. So more often than not, you have none in your field of vision, and you never have two. Keep that in mind when you draw. But of course, other vanishing points are still on the view plane, drawing in edges. Remember, a cube has 6 true vanishing points. At least one of them always lies behind you and you cannot see him or place him on the view plane or on the canvas. 3 to 5 will always be somewhere on the view plane. If there are 5, this means you are looking right away at one of them and the others are in infinity. Notice that when one vanishing point is in infinity, its counterpart on the other side appears. That's why it's possible that there are 5 vanishing points at the same time. Although there are so many, this is the easiest case, because it means there are many parallel lines, and only the vanishing point you are looking at radiates guidelines in different directions. If you ignore the outlying vanishing points, you are what is called often one-point perspective. Similarly easy it is when there are 4 vanishing points on a view plane. This happens when you are looking perpendicular at one guideline. The vanishing point corresponding to this guideline lies in infinity then, and therefore its counterpart is there and they emit parallel lines. This is often referenced as two-point perspective. And finally, when you are not looking perpendicular on any guideline, basically if you look randomly into space, there are 3 vanishing points on the view plane and they are not in infinity. You might even have one in your field of vision or on your canvas. This is the 3-point perspective. Here is a quick recap on all of them. From now on, in the cases of 4 or 5 vanishing points, where some of them lie in infinity, I will not mention their counterparts in infinity on the opposite side anymore and refer to them just as one vanishing point or the vanishing point. Also, these cases of 1 or 2-point perspective are easier because of all the parallel lines, so we will rather focus on 3-point perspective. Now I want to show you rules on how to use the vanishing points properly. Based on the clear position of vanishing points on the infinite sphere, you obviously can't just spread them arbitrarily over the view plane and start drawing. Here are 3 examples where something went wrong. To avoid these mistakes, I present you some rules. Our approach will be like this. First, we will place the vanishing points and determine from them where the canvas lies and how big it is. Then we go the other way around. Start with a canvas and look where the vanishing points can be. There are 3 rules and 3 causes of these rules that will answer all these questions, and all of them can be deducted from this geometrical model. Let's go. Let's place 2 vanishing points on a view plane. Somewhere on the view plane will be the other vanishing point and the canvas, and these we want to determine now. Here comes the first rule. The triangle of vanishing points has no angles greater than 90 degrees. That means the third vanishing point can only be in the blue area or on its rim. All triangles that are produced this way are valid vanishing point triangles, and triangles that are not produced that way are not valid vanishing point triangles. This rule rejects our first bad example. Now we know where to set the vanishing points. But where can our canvas be? Where can we draw now? One part of the answer to this question provides rule number 2, which goes as follows. The middle of your image is the orthocenter of the vanishing point triangle. In case you don't remember from school, the orthocenter of a triangle is the intersection of its altitudes. On this way you can easily determine the middle of your image. From now we will refer to the middle of the image as center point. Rule number 2 rejects our second bad example. The altitudes are here, and that means here is the center point. The guy, whoever it was, started drawing in the wrong area, and therefore the cube looks a little unnatural. Now we know the middle of our canvas, which leaves only one question open. How big can the canvas be? How far can you draw now in order to not exceed our appointed 60 degrees viewing angle? The answer to this is rule number 3, which is the formula for the radius. So we need to take an altitude and divide it into v and w. Then we multiply these, divide it by 3 and draw the root. Let's do this. I measure 8.5 for v and 4.5 for w. If we insert that into the formula, we get about 3.5. So for this set of vanishing points, the radius of the canvas at 60 degrees viewing angle is about 3.5, which means we can draw about this far if we want to stick with these 60 degrees. If you want another viewing angle, here is the more general formula for the radius. Here you additionally have to calculate tangents of half of your viewing angle alpha. And by the way, you could have also taken one of the other 2 altitudes as the product of v, and w is always the same in a triangle. Okay, probably some of you are wondering why 60 degrees. Isn't that completely arbitrary? We will get to that now. By controlled coincidence, this vanishing point triangle resembles the bad example number 3. Rule number 1 is fulfilled, and here we have the center point. The cube close to him looks quite natural, and the one besides him may also be okay. But the farther you move away from the center point, the more a distortion will kick in. I'm sure you agree that the third cube doesn't look good or convincing anymore, and if you continue to draw cubes, they will be even more distorted. You could do that, it's absolutely possible and consistent with linear perspective, but it will look very strange. Here we have a shot from a camera with a wider angle. It's kind of a mix of fisheye and linear perspective. The cars on the right already have a distorted look, and if it was clean linear perspective, the distortion would be even more obvious. So yeah, it is possible to have wider angles in linear perspective, and of course you could draw on as much as you like with your vanishing points. But as you saw, at one point it starts to look unnatural and distorted. Of course, there's no absolute law on how far you should draw, but these 60 degrees may provide a nice reference. My researches about natural viewing angles said something about 53 to 60 degrees, and that also corresponds to my experience. My mobile phone camera has an angle a little above that span. In the end, I settled with 60 degrees because then tangents gives a nice number. So yeah, this is just a rough reference, and it really doesn't matter how far you draw as long as it looks good. Just keep in mind that you can't draw on and on if you don't want too much distortion. Now let's briefly go back to the situation where we already placed 2 vanishing points. What if instead of the third vanishing point we were to place the center point first? From rule number 1 and 2 it follows that the center point can only be in this circle or on its rim. Let's set him for example here. Doing so uniquely defines where the third vanishing point has to be. From rule number 2 we already know that the third vanishing point must lie on this perpendicular line. You just need to place him in a way that the altitudes go through the center point. And if you really want it accurate, you can use this formula, which is also a cause of rule number 2. X is how far the vanishing point must be up this line, and we can calculate it by multiplying A and B and dividing it by W. In our case, X is 9.3, and that means the third vanishing point is 9.3 units up this line, which is here. So now we determined the third vanishing point from the center point. And from here you can again determine the canvas like before. Okay, now we saw the way from vanishing points to the canvas. We saw that we can place 2 vanishing points arbitrarily, but then restrictions apply. The center point can only be in the red area, and the third vanishing point can only be in the blue area. And once you set one, this uniquely defines the other. However, often you are in the somewhat opposite position. You drew a scene on your paper and you want to add a cube to help you, let's say, draw a building. That means you choose your canvas and its size, and now you want to know how the edges of the cube go and therefore look for its vanishing points. That is the second situation we want to cover. For convenience, let's go again with a circular canvas, and here we have the center point. Now it is similar like before. The first vanishing point you can choose completely arbitrary, but after that restrictions apply. Here you may think about rule number 2 and try to set the 2 other vanishing points in a way that the altitudes intersect in the middle of your image. Or if you want it more accurate, you may remember the situation from before where we calculated the size of the canvas with rule number 3. Now we have given V and R and we can rearrange the equation to get W. In this case, W is equal to about 4.1. Now rule number 2 says that this line is an altitude and hits the side of the vanishing point triangle perpendicular. That means the other 2 vanishing points lie on that line. And if you set one, you can determine the last one just like before. Isn't that hard, is it? Here we have all rules and all causes at one glance. If I was you, I would mainly remember rule 1 and 2 and maybe also cause 1. They are quite easy to remember and probably already have a remarkable positive impact on your perspective drawings. Concerning rule 3, from my experience, intuition usually serves well enough in that place. I decided to include it because some people might want to know it that accurately, and also because the derivation was a nightmare. Cause 2 and 3 are very situational. I think with these I covered all the different approaches that you may take concerning the order in which you choose vanishing points and the center point. But as I said, I would mainly remember rule 1 and 2. No one likes calculating, and if you follow just these 2 rules, there already is not much left that can go wrong, I promise you that. And of course, if you are just up to getting perfect perspective fast, then instead of following my rules, you might simply go to Minecraft or Blender for example. Turn in the direction you want and use this as your perspective grid. By the way, this approach also covers the cases where 1 or 2 vanishing points are infinitely far away. This is represented by the canvas becoming very small, converging to 0. Then this is basically the same as if the canvas was normal sized, but the vanishing points are infinitely far away. It happens if you set, for example, the third vanishing point close to the rim. Then rule number 3 gives a very small canvas, which is very unhandy. However, the vanishing points moving far away also means you are moving closer to 1 or 2 point perspective. And that means the lines are almost parallel, which is easier to handle. Like, the harder it gets, the easier it gets again. But still, having vanishing points that are out of your paper are annoying.
Here comes a technique that you can use to deal with this problem. You don't actually need to extend your paper if you know and can imagine where a vanishing point lies. His location can be indicated by two lines, and where they meet, the vanishing point is. Having those lines, you don't actually need the vanishing point anymore, because they already have all the information you need. Now you can draw any guideline you want. They just need to radiate in the same way from the vanishing point, even if you cannot see him. And you can get an intuition for that. By this method, you can draw according to vanishing points, even if they are very far away. And of course, you can do the same with the other two vanishing points of a cube. That means these lines can substitute for potentially unhandy vanishing points. And for example, a cube contains enough lines to substitute all vanishing points, as he has several lines towards each of them. So a cube can help you to establish your whole scene. This is also how I am drawing. For obtaining the cube, you might do a little thumbnail with my rules. Or, as I said, you might reference, for example, Minecraft. Or, what is even better, and what we will try in the follow-up video, you learn to draw the cube from intuition. Kim Jong-gi, for example, said his progress significantly accelerated after he learned to spin the cube. Okay, now you learned a lot about the theoretical use of vanishing points and how you can deal with vanishing points that lie far away. Let's add some more practical tips to it.
One thing you should always be aware of when drawing is the horizon. The horizon is the set of all vanishing points corresponding to lines parallel to the ground. He is a horizontal line on the viewplane, and he is not necessarily in the middle of your image or on your image at all. This depends on where you are looking at. On the infinite sphere, he would correspond to the equator. He is the most common set of vanishing points, but one might also consider vertices, etc. A cube standing on the ground has two vanishing points on the horizon, and one on the vertical line through the middle of the image. Many objects of the real world have vanishing points in that fashion. Yes, even people, for example here, the line through the ankles is parallel to the ground and therefore its vanishing point is on the horizon. The same goes for the two knees, the two shoulders and whatever else is parallel to these lines, like for example the piano. They all are hitting the same vanishing point on the horizon. Pillars, for example, I assigned to vertical lines, but if you set them in a row, this row also vanishes in the horizon. And of course, the same happens for other identical objects that are aligned in this way. You can even use vanishing points at a curved street. If you stood here and want to draw it, it may be quite hard to know how it winds over the paper. But you have the horizon and you know, at any segment its parallel sidelines must point towards the same point on the horizon. Let's say you drew the horizon and one side of the curved street, and let's assume the street is that broad here. Now the sides at this point are physically parallel and they are parallel to the ground. That means they point to the same point on the horizon. If you do this 2 or 3 times, you should have a good impression about how the street is going. And by the way, the horizon is always on the eye level. The camera is on the same height as any object that lies visually on the horizon. Alright, that's it about the horizon. Here I have briefly some more facts and tricks and implications for you. Okay, that's it for this video, finally. I apologize for such a long one, but perspective is one of the hardest aspects in art to grasp, and I didn't want to spread the theory over several videos. Also, at some points it became quite mathematical. What do you think about that? Does it destroy art for you to tackle it with such an approach? If so, I'm sorry. Just forget the formulas then, you don't need them. Now briefly, one last time, theory is nice and handy, but you should set your goal to get intuition for perspective and spatial imagination.
Kim Jong-gi, I strongly reckon, doesn't know my formula for the radius, but as he said, he learned to spin the cube. We will try to learn that too in the next part. See you there and keep drawing. And if you draw something following my rules, please do share it, I would love to see it. Bye!